Hi, my name is Holden Rogers. I'm from Raleigh, North Carolina, and next year I'll be a rising junior majoring in chemistry and mathematics. And you want to know why I want to be a mentor? Well, to be honest with you, when I first started here at Carolina, if someone asked me whether I wanted to be a mentor in a chemistry course, I would have probably said no. But what really changed my mind is the fact that the mentors that I've had over the course of my 4 semesters here have really impacted how I understood the material. For example, in Orgo 1 and 2, I was lucky enough to have Omar as a mentor, and he really helped me understand the material on a deeper level, which really contributed to my success in the class. And the reason why I want to be a mentor is because I want to give back all the knowledge that I've accumulated over these chemistry courses, and I believe that I can help struggling students just as Omar helped me in the past. And I'm really excited to get started.
Okay, so we have an example here, and it asks us to draw the major products of the following electrophilic addition reactions. So just to get started, let's just discuss what we know about the problem. So we have 3 different alkenes as the starting materials, but for each one we have the same reagent in HCl. Also, the question says that these are electrophilic addition reactions. So by now, you should know that in these types of reactions, the first species that adds the reactant is an electrophile. So our next step here would be to determine which part of the HCl is the electrophile, and so to determine which one we'll add first. So over here, I'm just going to draw HCl, and from Gen Chem, everyone should know that chlorine is the most electronegative out of these two, so it's going to contain the partial negative charge while hydrogen contains the partial positive charge. And knowing that an electrophile is something that is electron deficient and it wants electrons, we know that the partial positive charge is going to be the electrophile in this scenario. So going from there, we know that hydrogen is going to add first to these alkenes over here, and with that we can determine where in each of these the hydrogen will add. So we always know that the hydrogen adds to the least substituted carbon in order to create the most stable carbocation. So the next step here that I like to do is just to label each of the carbons in the alkene, whether they're primary, secondary, or tertiary, because this is going to help determine whether the carbocation that's going to be formed is stable or not. So just starting off with A, we'll go through all of them. Starting off with A, we know that this is secondary carbon right here because this carbon right here is bonded to 2 other carbons. This carbon here is tertiary, which means that it's bonded to 3 carbons, 1, 2, 3. Okay, moving on to B, we see over here that this is a primary carbon because it has 2 hydrogens coming off of here. And we know that this is a tertiary just as this one was up here because it has 1, 2, and 3 carbons. Moving on to C, we have a primary carbon here and a secondary carbon here for the reasons stated above. This one's bonded to 2 carbons and this one is bonded to 1 carbon. Okay, so now that we have them labeled as primary, secondary, and tertiary, the first 2, A and B, are fairly easy to finish off here. So we know that the hydrogen adds to the least substituted, and then following that, the chlorine will add it to the most substituted. So we can just finish these off like this. So the hydrogen is going to add to the secondary, so we're going to have a hydrogen there. There's already a hydrogen there as well, so there's going to be 2 hydrogens on that one. And then the chlorine will add to the more substituted side, the tertiary side. For the second part here, the same thing occurs. The hydrogen will add to the least substituted side, excuse me. So we will have 3 hydrogens off of that carbon there, and then the chlorine will add to the most substituted side, which is there. So we will have that. Now this third part, C, is a little trickier. So before we finish the products, I'm going to move to this bottom part down here where we discuss the mechanism of C. So knowing that what we know already, we know that the hydrogen is going to add first. So let's go ahead and draw our arrows. So our arrows are going to go from the double bond to the hydrogen. Remember, you always go from where the electrons are to where the electrons are going. So we're going from the double bond to the hydrogen. So that's going to take the hydrogen off that, and then we're going to draw that arrow like that in order to get the hydrogen off the chlorine. So now we can draw our next part here. So we have our hydrogen adding here, and there's already 2 hydrogens there, so now we have 3. And now we have our carbocation intermediate, and this is very important because this is where part C differs from part A and B. So we have our carbocation intermediate, and right now it's on a secondary carbon because we know that this is our secondary carbon here. Now, in terms of stability, secondary carbocations are more stable than primary, but they're not as stable as tertiary. So what we can do here is something called a hydride shift, and in a hydride shift, we're going to shift a hydrogen over to the positive charge in order to get that positive charge on a more stable carbon. So we know that there's an extra hydrogen here, right? So what we're going to do is we're going to move this hydrogen over to this positive charge through a hydride shift. And what this will do is this will make our carbocation more stable. And in chemistry, we're always looking for the most stable reactions, so this is something that's going to be favorable. Something to note here is that this only occurs if it's more stable. So we're not going to do a hydride shift to go from a secondary carbon to a secondary carbon, but in this case, we're going from a secondary carbon to a tertiary carbon, because what's going to happen is this hydrogen is going to move over to the double bond, to the secondary carbon, and then what's going to happen is we're going to have our carbocation on the tertiary carbon, and we're going to have our hydrogens here. So, as you can see here, this is very similar to what the mechanism would look like in B. So we have our carbocation on the 3rd carbon, and so what's going to happen is we have our chlorine over here, and our chlorine is nucleophilic because it has the negative charge here, so it's going to want to go towards that positive charge, and it's going to add there. So then our final product will look like this with our chlorine off of that. So we can come back up here and draw our final product. And if you look at all 3 of these, A, B, and C, what you'll notice is that all 3 of them are the same. They're all the same product. If you remove the hydrogens and you just put the most important parts here, and you can see that all 3 of them are going to look like this. So this is something that's really important in Orgo 1 and Orgo 2, is the realization that there's multiple ways to get the same product. So, knowing this, that's how you do this problem. We have the electrophilic addition of 3 alkenes, different alkenes, in fact, with the same reagent, and we get the same product. And the key here is to understand that tertiary carbocations are the most stable, so when you don't have one, as you do in A and B, when you don't have one in C, something's going to occur like a hydride shift. There's also something called a methyl shift in order to get that positive charge on the tertiary carbon, which makes it more stable and more energetically favorable. So that's this problem here. Hope it helped, and thank you.